In this section, I want to look at primality testing. How do you test for whether a given number is a prime? And introduce pseudoprimes and Carmichael numbers. First, we'll look at the brute force primality test. That's where you just test for divisibility by primes up to the square root of n. Give you a composite number test where it will allow you to conclude that a number is composite, but it's not going to be an if and only if test. We'll define pseudoprimes, Carmichael numbers, give you Korselt's criterion for when a number is a Carmichael number, talk about Lucas's primality test, and then the strong pseudoprime primality test. Okay, the very basic primality test is what we did back in grade school. If you want to test whether a big number is a prime, you start testing for small prime divisors. And the claim is if the number has no prime factor less than the square root of the number you're testing, then n is in fact a prime. And I think this was on an early homework problem. So the idea is if n is a composite number, then n equals a times b, and one of these two factors has to be at most the square root of n in size, and so it must have some prime divisor at most the square root of n in size. So that's all that's going on there. That was a homework problem. And this test is nice because it's really an if and only if statement. Certainly the converse is true. If n is a prime, then it has no prime factor, at most its square root. The next test is a one-directional test. So a positive outcome allows us to conclude that the number is composite, but a negative outcome is inconclusive. So if we have a number m, a positive integer, and another integer a that's not divisible by m, if a to the m minus 1 power is not congruent to 1 mod m, then I conclude that m is a composite number. And it's a very simple test to prove. So, proof by contradiction. Suppose m is a prime. Then since m does not divide a by Fermat's little theorem, a to the m minus 1 power is congruent to 1 mod m. A contradiction. Contradicting our assumption that it's not congruent to 1. Therefore, m is not a prime, m is composite. Simple as that. There's another way you can phrase this theorem. You can say if m is a positive integer and a is another integer with a to the m minus 1 not congruent to 0 or 1 mod m, then m is composite. So I can leave out this extra hypothesis right here, and the proof is exactly the same, proof by contradiction. Suppose m is a prime. Case 1, if m is a divisor of a, then a to the m minus 1 would be 0, and if m is not a divisor of a, then a to the m minus 1 is 1. Now one might ask whether there is a converse to this statement, and unfortunately no. You can have a composite number with a to the m minus 1 coming out to be congruent to 1 mod m. So let's take a look at that concept next. Now in general, if m is not a prime and a is relatively prime to m, we do not have a to the m minus 1 coming out to be congruent to 1 mod m, like we have for the Fermat's little theorem for primes. However, sometimes that will happen, and when it does happen, we give the following definition. So if 1 holds, we call m a probable prime to the base a. So it's behaving just like a Fermat's little theorem in this case. If m is composite and 1 holds, then m is called a pseudoprime to the base a. So it's behaving like a prime, but it really isn't a prime. So it's a pseudoprime. And then a number m is called a Carmichael number if it's a pseudoprime to every base relatively prime to m. That is, the FLT relation right here holds for all a relatively prime to m. Now the natural question to ask is that possible? Can we have Fermat's little theorem holding for a composite number for all values of a? So it's quite reasonable to ask whether such numbers exist. And there's a simple criterion called Korselt's criterion for characterizing such numbers. So m is a Carmichael number if and only if m is square free, and for any prime divisor p of m, p minus 1 is a divisor of m minus 1. And so to look for Carmichael numbers, we try to find numbers that have this type of divisibility criterion. I'll let you prove the theorem in your homework, but here are the first few examples. 561, 3 times 11 times 17. So 3 minus 1 is 2. That's a divisor of 560. 10 is a divisor of 560. And 16 is a divisor of 560. So the criterion holds, and 561 is a Carmichael number. So these are the first 3 Carmichael numbers then: 561, 1105, and 1729. And so, now that we know they exist, what's the next question you ask? How many are there? Finitely many or infinitely many? And it wasn't until recently that this question was answered. Turns out there are infinitely many Carmichael numbers. This was proven by Alford, Granville, and Pomerantz in 1992, and they did it by counting how many Carmichael numbers exist up to a given value x. So let's call that number c of x. And they showed that c of x is strictly bigger than x to the 0.29 power. So a value a little bit less than the cube root of x. And naturally, as x goes to infinity, this number goes off to infinity. And so you do get quite a few Carmichael numbers sitting out there. So, if a to the m minus 1 is congruent to 1, we do not get to conclude that m is a prime number. However, if we strengthen the hypothesis, we get what's called Lucas's primality test. So suppose that we have an integer a greater than 1, such that a to the m minus 1 is congruent to 1 mod m, but a to the d is not 1 for any proper divisor of m minus 1. In that case, we do get to conclude that m is a prime number. So that's the type of converse statement we have to the what I was calling the composite number test a couple slides earlier. We need this extra hypothesis here. Proof. Well, let's first note that condition 1 implies that a and m are relatively prime, because a to the m minus 1 is congruent to 1 mod m. Okay, so a is relatively prime, so we can talk about its order mod m. So let's let n be the order mod m of a. So condition 1 tells us that n divides m minus 1. And condition 2 tells us that it can't be any proper divisor, that n is not a proper divisor of m minus 1. Well, that gives us only one choice. N would have to equal m minus 1. Now, we also know that the order of any element is a divisor of the group order. So we also know n is a divisor of the Euler phi function. That's the group of units order. So m minus 1 must be a divisor of the Euler phi function of m. But phi of m is at most m minus 1. And so m minus 1 is a divisor of a number that's at most m minus 1. That would tell us, in fact, that phi of m has to equal m minus 1. And what does that mean? That means that every number smaller than m is relatively prime to m, which means that m is a prime. QED. Okay, when would I want to use Lucas's test? So it's particularly useful, and I've just repeated the theorem on the top here. It's particularly useful when the factorization of m minus 1 is simple. Let's take this example. Suppose that the number we're testing is 1 more than a prime power, so p to the k plus 1 for some prime p. Then what does this say? Okay, so then a to the m minus 1 congruent to 1 mod p is equivalent to saying that a to the p to the k is 1, not mod m, I should say, mod m. And then this one for all proper divisors of m minus 1 that would just be equivalent to saying, well, what are the proper divisors of m minus 1? They're just the powers of p smaller than p to the k, so p to the k minus 1 not congruent to 1. It would all boil down to, because knowing that this one is not congruent to 1 means that all of these smaller powers couldn't be congruent to 1. So you get a very simple test then for primality here. Next, let's look at the strong pseudoprime primality test. So I'll let m be a large integer we wish to test for primality. I'll factor m minus 1 as 2 to the k times d, where d is some odd number. So I pull off all of the powers of 2. And let a be a positive integer bigger than 1. A is going to be the base value that we're working with here. And I compute the sequence of values a to the d, a to the 2d, a to the 4d, all the way up to a to the 2k times d. So this final value is a to the m minus 1 power. There are 3 cases to consider. Suppose that a to the 2k to the d is not 1. So this means that a to the m minus 1 power is not congruent to 1 mod m. Then by our composite number test, we know immediately that m is not a prime. Case 2. Suppose that this comes out to be plus 1, and then you go back in your list. So this one came out to be a plus 1 here, and then you go down your list, maybe this one's a plus 1, and you let j be the minimal power of 2, such that we get a plus 1. So you get plus 1s all the way down the road, and then the next smallest one we want to test whether it's a negative 1. So j is going to be the smallest value where you get a plus 1. And if the next smallest one does not come out to be negative 1, right here, then we get to conclude that m is not a prime. And why is that? Well, if m was a prime, and x squared is congruent to 1 mod m, what's the conclusion we've seen? We've seen, therefore, x has to be congruent to plus or minus 1 mod m. And in this sequence here, as you're going from one term to the next, you are squaring the preceding term. So if you have a 1 right here, then the previous number would have to be a plus 1 or negative 1 if we really are dealing with a prime modulus. So we get another conclusion here that m is not a prime. Now if both cases fail, we're in case 3, that would mean that a to the d power is 1, or there is some value of j such that a to the 2 to the jd is 1, but that the previous one is negative 1, then m is called a strong probable prime to the base a. So it's again behaving like a prime. In this case, if m happens to be a composite number, then we call m a strong pseudoprime to the base a. Okay, let's look at some examples. So let's test 1387 for primality using this test. So step 1 is you factor m minus 1, pull off the biggest power of 2, which in this case is just 2 to the first power. Calculate 2 to the 693 power, that comes out to be 512. And then when you square both sides, this comes out to be plus 1. So we do have the Fermat-Little theorem type of relationship. So it looks like 1387 is a probable prime to the base 2. However, this predecessor fails to be negative 1, fails to be a plus 1 or negative 1, which means that 1387 must be a composite number. Next example, 1,373,653. So m minus 1 is 2 squared times 343,413. So again, I'll start with base 2. I calculate 2 to this value right here, and that comes out to be 890,592. Square both sides, and I get negative 1. So all of this calculation I did on a computer. And then squaring both sides again, I get plus 1. So what do we conclude here? Well, this time it's behaving like a prime at this stage. Still, m is behaving like a prime because I got a negative 1. So these two together say it's a strong probable prime to base 2. So m is a strong probable prime. Next we go on to base 3. I do 3 to this power. It came out to be a plus 1 mod m. And then you don't even need to go beyond that, because when you square it, you'll still get a plus 1. And so it is behaving like a prime again. Strong probable prime to base 3. So we go on to the next base, which is 5. This time 5 to the 343,413 is this value. Square both sides, I get that one. Square both sides, and you are way off. We don't even get that it's a probable prime to the base 5. So here clearly fails to be a prime. Fails to be a prime. So M is composite. So that's the idea of the test. You just keep increasing your base until you get to make a decisive conclusion. Now let's let SPA denote the set of all strong probable primes to the base A. It can be shown that if M is smaller than 2047 and M is a strong probable prime to the base 2, then M is in fact a prime. So 2047 is the smallest composite number which is a strong probable prime to the base 2. If M is less than this value, the one we just looked at, 1,373,653, and it's strong probable prime to the base 2 and to the base 3, then it is conclusive that M is a prime. Now this is a theorem that we're not going to prove here, but one can show that. So the number we were testing is the smallest number that's in SP2 and SP3, and that's why we had to go up to test the base 5 as well. And you keep going. If M is less than 25 billion, then with the exception of this one value, if it's SP2, SP3, SP5, and SP7, so you test 4 bases, you get to conclude that M is a prime. Again, that's a theorem that we're not going to prove here. So any number up to 25 billion can be tested for primality with just 4 applications of the above test. If in addition we throw in the base 11, we can go up to 2 trillion. If we throw in the bases 13 and 17, we can definitively test any value up to 10 to the 14th. You may be interested in knowing out how I carried out some of those big mod powers. I just used Wolfram Alpha. So just go to Wolfram Alpha on your website here and just type in whatever you like. So if I want to calculate 2 to the 343,000 power, I go 2 raised to the 343,413, and I was doing that mod 1373653, and you don't have to worry a whole lot about syntax here. It's usually pretty good at figuring that out. Let's see what it gives me. Okay, 890,592. And then we wanted to square that value, so I'll just come up here and multiply by 2. Enter. $1,373,652. So that's where we got congruent to -1. And so we concluded eventually that this was a composite number. So let's see how it factors. Let's see if I can be more clever. Keep all that, and let's just delete and say factor. Factor. Yes, it even put it in right there. But let's go ahead and type enter. Factor 829 times 1657, a product of 2 distinct prime factors, and it even lists all of the divisors.